Hello. Check, check.
Hello. Yeah. So, good afternoon and welcome everybody. I hope you all are not very tired after the exciting visit to TFR. Was it exciting? Only I am saying it was exciting. Okay, so welcome to the third special lecture of VV 2025 Physics. This is a special lecture, as you know, and this is in the memory of late Bimla Buti. So I would take a few moments to tell you about her in case some of you may not know about her. So Bimla Buti was born in Lahore, that time in integral India, and she studied there her early education. Then she moved to Delhi during partition and completed higher education there. With a very strong family support, especially from her father, she went to Chicago to do PhD. She did a PhD in 1962, so many years back. So just see, under the supervision of Professor S. Chandrasekhar, who, as you all know, because of Chandrasekhar, was limited. She is one of the most distinguished physicists, globally acknowledged for her fundamental contributions to understanding of chaos. Internationally known as authority on nonlinear dynamics, her work found applications in widely varying plasma systems, including astrophysical plasma. She was the first woman physicist to become INSA Fellow, and she founded Plasma Science Society. She worked in many organizations, Delhi University, IIT Delhi, NASA, and finally spent most of her main workplace work was PRL Ahmedabad. In addition to all her physics achievements and all that, she was well known for her strict discipline and her way of work. She served as a director of ICTP Plasma Physics Schools for a very extended period of time, featured in Indian Women in Science, and she always, on any opportunity which provided, emphasized the need for promotion for men in science. We were fortunate to have her address our VV students in 2020 in the first edition. It was an online lecture, and that's available to you on the YouTube. So please look at it if you haven't done. She had many awards, and I wouldn't go through all of them because for you to see. She was an exemplary role model for many young scientists, especially women. And I want to highlight her message to one and all was always, don't give up. This she has said even in that lecture. If you look at it, I was fortunate enough to have met and interacted with her briefly. Mainly because when I was working for Indian Physics Association, and she was associated with it in many ways, and we had an opportunity to meet her in the conference in 2019, and it was very, very inspirational. She founded Buti Foundation after her retirement and got into philanthropic activities. There's their webpage address, and they have a multiple dimension. They have initiated number of awards through scientific institutions and societies, and they also have centers for digital education of women and cancer treatment, so on. VV 2025 Physics TIF and TIFR are sincerely thank for Buti Foundation for generous support to Gyan Vidushi program. As you know, we have since last year this memorial lecture in her honor of Bimla Buti, and also we have support to have selected three project students, which will also happen this year. And today's lecture is also supported by them. So that also brings me now to introducing today's speaker. Very aptly, we are also going to hear about chaos. It's a great pleasure and honor to introduce Sudeshna Sinha, who is currently at IISER Mohali. Sudeshna was my senior when I was doing my PhD here, and I always stood in awe of her academic excellence. As a person, she is extremely friendly, and we were all you will also find that out soon. So she got her PhD from TIFR here under the guidance of Ram Ramaswamy. She has been a faculty at IIA, that is Indian Institute of Astrophysics, Institute of Mathematical Sciences, and is currently a professor at IISER Mohali. She has served there as a deputy director also. Her work in the field of nonlinear science, chaos, and complex systems is widely acknowledged, and she has several patents. She is a recipient of the Birla Award for Physics and was conferred J.C. Bose National Fellowship. She's been elected a fellow of Indian Academy of Sciences, Bangalore, Indian National Science Academy, New Delhi, INSA, and the World Academy of Sciences, Trieste, and many more things. Without much further ado, over to you, Sudesh.
That helps, yeah, to turn it on. That is, yeah. Okay. Right. So first, I should say it is indeed an honor to deliver Bimla Buti Memorial Lecture, and not just because she was a pioneering plasma physicist, which Vandana has already told you about, but because she was really a relentless champion of women in physics. She never gave up. I have never heard her, at any point, give way to, what she believed. She really took it to the logical extreme in a perfectly, in a way in which we don't expect women to do typically. So I always absolutely admired that in her. This don't give up was so true. She embodied it. And I should also say that it seems absolutely appropriate to give this talk to an audience full of young budding scientists. It's not actually a typical audience I end up giving talks to. I mean, the gender ratio is wonderfully skewed in in a way which I'm not used to, and it's great to see that. And I should also say that I did not have personally the good fortune of interacting much with her, except in those, committee meetings where she did not give up in a good way. But still, Professor Buti's influence was really profound, because in some sense, the way she navigated her life was an embodiment of the word empowerment. Now we use these words a lot, empowerment and stuff. Just the way she lived it was an embodiment of that. And there are all these, Lakshman Rekhas, conscious, unconscious, which we give ourselves or which are perpetuated. She breached a lot of them. And all those gaps in the fence she made, we slipped in through that. So in some sense, we are all grateful for what came before her. Right. So I will not say much more than that about Professor Buti. Vandana has already said some. And I believe if any one of you want to talk to me after the lecture about, where my trajectory, where it started and, how it's chugging along, you're most welcome at tea time or dinner. So let me get to the topic at hand. And so what I will talk about is this concept of chaos. And then I will sort of go on to tell you how you can make it work for you. So somehow there's a negative connotation, like, chaos is something you want to do away with. And sort of I will try to flip the narrative and say, okay, maybe it also gives you an opportunity and, to be used for something useful. So that's what I will hope to convey to you. I will start off at the beginning, which, as we all know, is a very good place to start. My profound apologies to some people in the audience who surely know everything. I don't know why you're here, but this is my audience, so bear with me. So what I will do is I'll just outline some of the basic concepts which powered the concept of chaos. Okay. So here is a brief history of chaos, necessarily shallow, and I will start with a spin on Wigner's quote, and I think this is important. We really wonder even today how classical mechanics is so unreasonably effective. It is a quantum world, we all know it, we all accept it, but how is it so absurdly good? Why is it still a workhorse of not just the engineering sciences, but a lot of physics from nanoscale to astrophysical scales? So it has almost no business being this good. Okay. And it still makes me wonder, even when I'm teaching Physics 101, how does this framework, which is so old, work so well even now? Okay. Because remember, in this talk, I will be essentially only dealing with classical physics. And sometimes, classical is just a polite way of saying really old. And not to be ageist and all, some people think old is boring. So I hope to tell you that it is old, but there are new concepts there which make you sit up and rethink all the things which you thought were done and dusted. Okay, that will be the hope. And so this concept of chaos is a new frontier of a very old framework, a mathematically rigorous framework, a toolkit which has been there to understand phenomena over extraordinarily large scales. And in a way, it will make us reassess the way in which we look at the physical world, the classical physical world still. Okay. So one of the things which everyone, is motivated by is the future. Okay, it's an eternal quest, which is how astrologers make all their money. Everyone wants to foresee the future. And one of the beautiful things about classical mechanics is that it is deterministic. Okay. So which means I give it a state, it spits out the next state, and goes on forever and ever. So in some sense, this would imply that if I knew all the properties of the system, where system, quote unquote, could be a particle in a box, could be a ball in a billiard table, or many balls in a billiard table, as is more usual, or a weather system where, Avogadro number of particles. But whatever it is, this system, if you knew the laws of physics, we knew its state, you could perfectly predict its future because it's deterministic. It's by definition. So this is a concept which you can think of as a clockwork universe, right? But now, this is the surprise, unpleasant surprise, in fact. A very large range of seemingly very simple natural processes seem to be exhibiting extremely complex behavior. So it is so complex that, at first glance, it appeared to be evolving under maybe random forces and not even a deterministic law. Okay, so something simple gave something very complex. After all, if something very complicated gave something very complicated, where's the surprise in that? But the simple gave very complex. And the second delicious contradiction was this, that though it was completely deterministic, you didn't put any stochastic element, you didn't, it was perfectly clean system. In spite of that, it displayed this exponential sensitivity to initial conditions. So what I will go into that a little bit more. So in some sense, it was something which made predictions really bad. So it made the deterministic system effectively unpredictable. So you never thought you would use the word deterministic and unpredictable in the same sentence. But here we are. So this sort of necessitated some kind of a paradigm shift because you have to deal with, it's the same classical mechanics, same framework within which you have to understand this. So it's the, sort of a new ship in a very old block in some sense. So it gave rise to what we sometimes call a new science or chaos theory. I find it very interesting that the word chaos is used in English language, right? And in India, we use it all the time, for traffic, for politics, for, what have you. And it's a very apt word for most of the stuff that goes around. So we know the Webster meaning of chaos: confused, unorganized, disorderly. There are other synonyms. And it actually is a very old word. It has roots in Greek cosmology. And I found that Netflix has a series called Chaos, and I took a screen grab of that. So clearly it's a word which has trickled down to, popular imagination. Now, from this use of it in regular language, how did it sort of trickle down or make its presence felt in technical way? So here it is. The first paper, I think, as far as no one has contradicted me on this, is a 1975 paper by Lee and York, where the word chaos is in the title. This is an American Mathematical Monthly journal, and so it's fairly rigorous. It's called Period 3 Implies Chaos. So from being a word, so there's some sociology also in this, how something which invokes a certain idea in our head actually then gets a technical meaning. Okay, so does God play dice? Again, a spin on a very popular thing. So the first hint that nature could be both deterministic and unpredictable goes back to actually 1800s. So the King of Sweden offered a prize to anyone who could solve the so-called three-body problem. So you have, the sun and the earth, throw in the moon, or sun and the earth, throw in a big fat Jupiter, or whatever. So a three-body problem. And the French mathematician, Poincaré, won the prize in the manner of many mathematicians by not solving the problem. But he did tell us how he wrote about the problem and described the reasons why it could not be solved. A very important thing, actually. And so one of the most important reasons he highlighted was this, that if you have small differences in the beginning of the system, it would lead to big differences at the end. This is a colloquial way of saying it. Another way to paraphrase it, which I like a little more, is that the present determines the future. That's the definition of determinism. But the approximate present does not approximately determine the future. Okay, so that is where your predictability creeps in. Okay, then the advent of computers. So again, there is something which we sometimes don't take into account in the progress of science, how much technology actually comes and, gives it a certain push. So in some ways, some of these equations are all differential equations or iterated function systems. They are very, very difficult to do analytically or find exact solutions of. So the first thing is that you just leave it alone. You wait for some method which will come in 200 years maybe to solve it. But what happened was there were computers. And once they came in, you could numerically simulate these equations and get a sense of the solution. So what was a hard dead end, suddenly, which was a hard dead end for centuries, suddenly opened up. So in some sense, technology is absolutely squarely responsible for the advent of this field. And so it started, for instance, Lorentz, as a lot of stories have said, and it's kind of true actually, is that Edward Lorenz was studying a simple model of the weather system, and he had a computer because he was sitting in MIT, good for him. And another thing is that this field is extremely multidisciplinary. So he was in the earth and environmental atmospheric sciences, okay? He wasn't in the physics department. So in those days, things didn't run, the power would go off and stuff like that. So people would stop their simulation, take down the last result, and start again in the morning. Someone switches it on. And so he did that. But what he found was he got extremely different results depending on how many digits he kept in his last result. Okay. So he found that extreme sensitivity to initial conditions is what he discovered, because a tiny rounding error, not more than 1 part in a million, would lead to completely different behavior of weather in his model. So in some sense, he stumbled upon chaos. Okay, so remember, everything in life is finite precision. Whichever way you, whether you store it in your computer, whether you observe it with an instrument, whatever. The world is finite precision. So this is a very important thing. Okay. So now, if chaos was not very widespread, you can say, well, okay, there are some special systems that shows chaos. It doesn't bother me so much. I can stick to my corner. Certainly, engineers would be very happy to say that. In my corner, there is no chaos. But that is unfortunately not the case. For instance, if you, all of you, since you're in first year MSc, so all of you have done and have been tested on a simple pendulum, a two-body problem, central force problems, and it is something which you can do in, exactly even when you're starting out learning physics. So it allows precise formulation of these problems. But go up one step, just one step. Throw in your third body. Throw in one more bob in your pendulum. So from single pendulum, you go to a double pendulum. All bets are off. You will not be able to write down a solution in its most general way unless you do some approximations in a very, very narrow range, and you will have the possibility of chaos. So here is a thing which I took out of Wikipedia. It's a nice picture. So it's a long exposure of a double pendulum, and you can just see whatever else you make of it, it's very complicated. Okay, this much is there, right? After all, a simple pendulum is your standard timekeeper, we go back and forth, and here is your double pendulum doing all this for you. You cannot write an analytic form for this trajectory. That is also true. So I shall summarize. A slightly imprecise, maybe not terribly though, characterization of chaos would be a sustained, disorderly looking, I've not put that a little bit in quotes, aperiodic, that's certainly technically true, long-term evolution. And owing to this extreme sensitivity to small changes in initial conditions, its behavior is so unpredictable that it appears random. So if I had to give a precise signature, I would have to calculate this. Oh, I should use this. Yeah, so I will have to calculate this exponent. It's called a Lyapunov exponent. There is an exponential here. it sits out here. It tells you how fast two neighboring trajectories. So if you give a slight dhakka to your trajectory, how fast they're going to fly apart. And that is sort of captured by the exponent of this exponential here. So this object, if it is positive, it is going to imply chaos. This is actually the technical definition of chaos. And here is a movie poster which I found called the butterfly effect, which sort of is a kind of a popular way of saying this, that there is a small flutter here, and the small flutter or jitter gives you this enormous thing really soon. So it blows up in your face very soon, whatever little difference you had. Okay. So now, how large does a system have to be to exhibit chaos? So, I mean, can I start really small and do it, or does it, what is the minimum number? So if I have n first-order autonomous ordinary differential equations, I need at least three or more to exhibit chaos. But there are other ways of looking at dynamics. And the other way is discrete time. If you think of it, it's actually a very, very standard way of thinking about it. So it's like a stroboscope. You see the state, then you see the state after some time, you see the state. In fact, all measuring instruments are discrete time in some sense. There's a sampling rate. And so if you do, that is a map. It's an iterated function equation system where you sort of put in a function and you iterate it. And this is your time ticker. Okay. If I do that, I actually need only two for an invertible map. An invertible map is when the function has a has an inverse, and which exists and is unique. I need only two. And if it is non-invertible, I can get chaos for as low as 1, which is essentially I can get chaos even with a single map. So you can imagine how simple the system can be in order to show chaos. Okay, so here is an example of that. Example of a one-dimensional nonlinear system, discrete time system. I put 3 of these here. And this is the dynamics. Okay, this is the state variable x, the real number, which is its state. And n is its discrete time ticker. Okay, 1, 2, 3, 4, it goes on. And this is the function. Very simple. It's just a parabolic sort of function. Then this is another function, very, very well known, called a shift map. I don't know if you know the mod operation. If you goes outside the range, you take the remainder and bring it back. So it's a piecewise linear function. This map is also a piecewise linear. So that's the simplest nonlinearity, as you have 2 straight linear bits, but they are piecewise linear, but not fully linear. So these essentially give the same look. And this is the look of the system. This is how simple it is. You can sit and, put it in your, I don't know, into your pocket calculator. I don't know if you don't carry that, of course, phone maybe, and get this time series. But if I just gave you this time series, you'll wonder where it came from. It could be just noise. It could be a table shaking. It could be some, I could have just got it out of my random number generator. So this is the surprise. Something one-dimensional, so simple, can give you this. Okay, that is the part I want you to take away. And I thought I'll give you a 2D map also, just to tell you that in classical mechanics also we have cats. It's not like those, quantum mechanics has sort of cornered all the cats in the business. So here is the cat map, and this is a 2D map. Again, there's a mod 1 operation. Remember, this mod 1 is actually, right now, it would be too much for you to understand it, but you can keep it at the back of your head. There is a stretching and a folding operation that is necessary for chaos. The stretching gives the Lyapunov exponent. The folding brings it back into a bounded region. Because if two things flew apart to infinity, it's not very interesting. The fact that it's folded back into phase space gives it all the complexity. So mod 1 is your fold, and this gives your stretch. If you can keep it at the back of your head. So, but from here you can see the first operation gave you a stretch. So first you get a stretched cat, looks like a cat, unfortunate, but still cat. But the next operation, where you fold it back into the square, gave you something in one operation. It looks like nothing like the cat. So all the information has been lost. In a very, very, so you can see how much scrambling has gone on. Okay. So now what I thought I would tell you is that, so here is a new way of looking at classical physics. can we sort of use this knowledge, this new knowledge? It's quite new because Lorenz is around 60s, then first time it came in literature is around 70s, and 80s is when textbooks started up. 80s, late 80s, textbooks started coming. So, it's somewhat new in that sense. So can we use this knowledge to work for us? Okay. Now, some sort of payback of the knowledge. Okay. So what is tempting about chaos? It has all these patterns. Clearly, a lot is going on. Things are going up, down, all any which way. And all these patterns are there. So if we could sort of control or use parts of this pattern, then maybe we can get it to do some useful work for it. Let's see how it goes. Okay, so perhaps we can use it for fun, maybe some profit if you're lucky. Okay, so now I thought I'd, I don't know, about how much time I should keep some idea. Okay, half an hourish, right? Yeah, so I thought I'd give you a sort of a light souffle version of a couple of ideas on how to use chaos to work for us. Okay, so what will I try? Now, I can keep using this word work for us, exploit chaos, harness chaos. They all sound nice and all. But the basic thing, the job a theorist or an experimentalist has is to control it. No engineer is going to buy a gadget or a device from you unless you show that it's a controlled bit of something. Okay, so I can't say that here it is, you try it in this wonderful vacuum chamber or something in a perfect setting and it should work. That is not how they buy your ideas. So we need control. So we need strategies to extract what we want from these temporal patterns. And I like this quote. Again, I will misquote it a little from von Neumann. It's a lovely quote, actually. He had said, all stable processes we shall predict, all unstable processes we shall control. The way I like to put it is all regular processes we will predict, and all chaotic processes we shall control. So just a small spin on von Neumann, but this is the basic philosophy. Okay, so the regular stuff, of course, you write your equations, you predict, and the rest we shall control. And the second bit, which if I have time, I would like to also say, is that there is another player in this business, noise. You can't escape it. Somehow, again, it's supposed to be something you suppress and, do away with. Can we sort of get it to work for us? Okay, so that will be the second thing. So let me start. So here is a control scheme. It's a very, very simple scheme. Remember, so in whatever you think, maybe I should keep my logistic map somewhere there. So remember, this logistic map, I'll just keep it on the board somewhere, was this function, okay, xn was, so let me take this version, okay. So I will keep this here, and this scheme, all it says is, so remember this x is in this range 0 to 1, okay. So if I look at it, this is my thing. So suppose I take an interval 0 to 1, this is xn. So xn plus 1 is this function, which is a parabola. So if you look at the parabola, at half it has a maxima at 1. And so this is the function. This is it. That's it. And so if I write a program, I can put in my xn, predict xn. Then I take the next one and I predict the next one. And so it goes. Now in this one, what I can do is I can say that if x is greater than x star, so it's like literally a Lakshman Rekha or a boundary in phase space, then I pull it back to x star. That's all I'm doing. Okay, so it's very, very simple conceptually, extremely easy to do in experiments. And so what you can do is you add very easy to do in a numerical experiment as well. So if x is greater than x star, I pull it back to x star. If it's less than x star, I let it do whatever it wants. Aram se. Okay, so this is like a thresholding, because I put a threshold like this far and no further. or some people I know like the word resetting, but I think we have been calling it thresholding. And it's a little bit of it's a dynamic range limiter. It limits your dynamic range. It clips some part, puts a wall in phase space and says this far and no further. But what does it achieve? What it achieves is that extremely complicated trajectory which I showed you, which looked like noise, really. If I did this to it, I would be able to clip it to exact superstable cycles. So from chaos, I get stable cycles of all orders. And the way you can think of it intuitively is that there is this trajectory. You sort of snip or prune part of it, stitch it together in a flat way so that you get parts of it that you want. So you're extracting patterns from this thing which has many patterns. And so why is chaos advantageous, and why are you even dealing with it? Why do you even want it? Now you want it because actually the chaotic trajectory has all these temporal patterns. If it doesn't have that pattern, you can't clip it, you can't extract it, right, if it's not there. So you need those patterns, and to get those patterns, you will have to deal with chaos. And so from that logistic map, which was all over the place, if I put various thresholds, I can get everything. Actually, I can get cycles of all orders. I can get a fixed point, which means it stays at the same point forever and ever. I can get period 2, means it just flips x1, x2, x1, x2 forever, stably. 4, x1, x2, x3, x4, x1, x2, etc. 6, 7, actually everything. And one can get a lookup table. And what is nice is you can calculate this lookup table exactly. You can do symbolic dynamics on this particular iterated function system and get an exact result, which tells you, given this threshold, what will be the exact cycle. And the slightly harder question, if I want a cycle, what thresholds do I give? That is it has multiple solutions, but it's still doable. And here is an experimental verification of it done by my friend Murali. He did it in his teaching lab. He had an analog of that system. And so all I did was give him the lookup table, which is from analysis, and he just plugged it in, and there it came. So here is this oscilloscope trace. So this was his chaotic trace, all this very, very noisy looking object. And when he put the right threshold, this particular one is 6. 1, 2, 3, 4, 5, 6. Repeat. 1, 2, 3, 4, 5, 6. Repeat. So this becomes that. And you can get any cycles of any order, no issues. So here is another one. From 1, you get 4. I forget what this is. 7 or something, 11, 12, something. So when Murali did it, it was low-tech, very, very low-tech, because it was a teaching lab, in fact. But later on, it's always good to still do a proof of principle experiment, because, you can get your friend to do it. And then once someone does it, the other people, feel they can invest more money and do it. And so later on, many people did versions of it. For instance, Morai's group in Japan did a CMOS circuit implementation of this, which had about 120 of these. But exactly the same thing, okay? Which Murali could do only 2 of, but they did hundreds of them. But the point is that in some sense, the underlying idea was the same, okay? You can do it for other circuits as well. This is a double scroll Chua circuit. Anyone of you have seen Chua? Very good. So if you've seen that on the oscilloscope, right? So if you could do a control experiment on it, you could put a little precision clipping circuit and you'll get it. You can get a fixed point, a 2-cycle, a 4-cycle, and all these things essentially come out from the same old chaotic system. So you can control it with great precision. You can do it with hyperchaotic attractors. This I will, if it doesn't make full sense to you, just bear with me for a minute. So there are these systems which have more than one positively Lyapunov exponents. So the way of understanding it is that the trajectories fly apart in eigendirections in more than one eigendirection. Now the thresholding you're doing is on one variable. So we sort of thought we are going to fail because, we thought we are putting a hard wall on one variable and the system is flying apart in other directions as well. But it somehow worked very well. And we don't have any explanation actually for this, but it does work and it worked even in the experiment. Okay. So now you have this. Can we sort of use this to do some very specific task now? This is not the only task. Actually, you have a very, very versatile pattern generator. You can do other things, but I will do this one task. It's a very important task. It is to make logic gates. Okay, logic gates are powering all your stuff, everything that you use from your laptops to your workstations. So chaos now to be used for computation. And what is the extra USP you want out of this? You would like your system to have the ability to switch between logic functions. Okay, so usually a static hardwired sort of architecture is built out of, all NANDs, all NORs, or something like that. But what you want to do is you want your hardware to have an ability to morph or to be reconfigured on the fly. So you'll have a dynamic architecture, the possibility of it. Okay, so that was the idea which we had. So an example, we have many, but this one is based on that one. Okay, take that logistic map. Okay, and now if you want to make, suppose I wanted to think of it as a 2 input, 1 output logic gate, I can have one explanation saying that, okay, the state of the system gets I1, I2, the 2 inputs, and, goes to some state X. And the output is just if it goes over threshold, it triggers 1. If it is below threshold, it's 0. And these are, for instance, the truth tables of a very basic logic operations, fundamental ones. NAND and NOR, of course, are fundamental logic. You can build any Boolean circuit out of them. But it's good to have all of them, because if you have all of them, I can switch between them. So how would that work? If I want it to work, I would actually have to solve or get a solution of all these equations simultaneously. Okay, these are the necessary and sufficient conditions which will give you all those logic gates. Okay, so the task at hand actually comes down to finding solutions. But do they exist? That's the question. They may not. The interesting thing is that the robust solutions of that set of things which I showed you exist if the system, and only if the system, is sufficiently nonlinear. So nonlinear is now working for you. Without it, you wouldn't have got that set of solutions. So in some sense, you're using that richness, all the power of the nonlinear transformations, and also the determinism, because that's what is allowing you to design it. And so now from the same module, you're getting all these different responses. Okay. And if I go on a bit, so here is a picture of it. I can say morph between NOR and NAND. So this is a control signal which I use to toggle. And these are sequence of inputs, I1, I2, the 2 input gate. And this gives the response which can switch between NOR and NAND. You can switch between any of them, of course. Okay. And this part was also picked up by a company, and they have some realization of it, which is pretty decent power and pretty decent size. They have sold out, which I believe is the ultimate goal of all companies, is to sell out to a big, very rich company, and hopefully Elon Musk will, buy you out or something. But anyway, so I think ARM Cambridge has bought it up now. Not think, I know they have. Yeah. So so some of it did get get featured in MIT Technology Review. Okay. So the last bit. So the last bit now is going to deal with another thing which we think of as undesirable: noise. Okay, just as you think chaos gives you these, feelings of, not a very controlled system, noise is also something which, is destabilizing. So this part is a question, came from a question which we kept getting asked, and that was that, there is this sort of fundamental noise characteristic, can't be suppressed, can't be eliminated. You keep making things smaller and smaller, you will hit it. So is there some way you can flip the narrative again and make the noise work for you? Okay. And since I like nonlinear things, I was thinking of how it might work for a nonlinear system. Okay. Not chaotic, nonlinear right now. Okay. So, so this thing was some ideas, which was trying to get a logic circuit which exploited nonlinearity in the presence of a noise floor. So in some sense, you should be able to do better in an optimal band of noise. So what would we do? And we called it logical stochastic resonance in analogy with the phenomena of stochastic resonance, where signals are in some sense amplified in an optimal window of noise. So if you take a signal to noise ratio, it actually is enhanced at some noise rather than only at zero noise. There is a noise which actually works for it. So in that sense, this is a logical stochastic resonance where the logic response is enhanced in an optimal band of noise. So here is a schematic. This ordinary differential equation has this nonlinear function here. This is not chaotic. Okay, this is an ordinary differential equation, one-dimensional, no chaos. Okay, but the function is such that it has two distinct wells. Say maybe x minus x cube or something. Okay, so you can have any other function. I'll show you a few. And here is your input, and this is the noise, which is your noise floor. Okay, so these are your input bits. This is your noise. This is your nonlinear system, this guy here, this f of x. And what this has two wells. So depending on the well, you can say that one is a 0, one is a 1. Every time you have two things, you can interpret it as a binary object. So I will think of this as a binary logic output. So this is the output, and its state is 0 or 1. And depending on the input bits, the noise, and its own transformation. Okay. And even if the rest of it doesn't make sense, just look at this for a few minutes. This is three sets of noise. This is low noise, this is moderate noise, and this is a lot of noise. Lot of noise we can rule out immediately. It's like no good. There's this, it's going here and there. So no one is going to look and be interested in an output like this. It's not consistent, it's not any good. So lot of noise is bad. That is a no-brainer. But you would have thought very low noise should be good. But it isn't. What it is doing is, it sort of is not responding to the inputs in a consistent way. Sometimes it's getting stuck in a wrong well and is not getting nudged out of it fast enough or ever. So in a sense, this is giving inconsistent, clean but inconsistent things. And somehow in the middle band, it's giving exactly what you want it to. So this is the bottom line, okay? That you have a logic output, consistent, reliable, only in this optimal window of noise. Not when it's too little, not when it's, of course, too large. That part is obvious, but in this moderate thing. And of course, since I have these two people who do very good experiments, whatever I pitch to them, they always have a little electronic circuit which does a proof of principle, quick experiment to show that it works. You can also use a bias, which people is a very simple thing. It sort of swings your well in a certain way. So, if you look at this is like a forcing function. If you look at the potential, you just integrate it out. It'll, swing your well one way or the other. And if you do that, you will be able to get different logic operations. This is the old idea of morphing and reconfiguring logic operations. But this is noise, and that is your constant bias. And this is the sweet spot here, this nice, bright little thing where the probability of getting your right result is almost 1. So you're getting the right result absolutely spot on with real full consistency all the time. So here is that sweet spot. So this is a moderate noise where it happens. And if I change my constant bias, I get either NAND or NOR. So I can morph between logic functions, and I can also sit in this nice spot. The spot is the same, by the way, about 0.5. And this is how you do it. So a couple of slides just to say that the idea, which is a very simple idea, which you can do and demonstrate with a differential equation, people can take it to labs, and that is why there is some power in simple ideas. So this was done in Mohanty's lab, and he has a nanomechanical oscillator. So remember my first thing about the unreasonable effectiveness of classical mechanics. So this is at nanoscales, okay, and it still works very well. And so he had two different vibrational states. You need two states, or at least a multiple number of states, to coexist in order to switch. And this is a noise-assisted nanomechanical logic gate. And so here it is, same thing, less noise, it gets stuck here and there, not giving you the right result. Here it's, no good. And in the middle, it's just perfect. It's a bit like Goldilocks and the porridge and the bed, right? It's just right. Okay. You can use all kinds of nonlinear functions. So now that you know it, one can try whatever is your favorite nonlinear box. So here was one with a synthetic genetic network, and you can use this. The good thing here was it had two variables. All this other thing had one variable. If you have two variables, you got to get something extra. You're doing extra work, you might as well get some extra, josh out of it. So what is the extra thing you can get? If there are two variables, you can get them to do two different logic functions in parallel. Then at least you're getting something out of it. So here we tried to get an OR and an AND in parallel for this system. Okay, one we got from one variable and the other from the other. So every time you want to apply things, if you put in something extra, make something more complicated, try and extract something out of it, because you should get something for your investment in a bigger and more complicated system. Yeah. So there are some popular articles on this, and some of this is written better than the way I'm explaining it. So you could have a look if you're interested. Yeah, and my student Vivek Kohar has a demo actually. He has made a very nice demo. I wish I knew how to do it online. I can't. But y'all, if anybody is interested, you can actually go in here and play with the well. So as I said, I can change the shape of the well in different ways and get the output. I think the only thing is I kept telling Vivek, I usually make time run this way and X goes that way, but he's done the programming, so it's his choice. So he has made X this way and time that way. Otherwise, it's there. So it's a very nice demo, actually. He's done a very good job. So far, this is essentially my last two slides. In this part, the nonlinearity didn't have chaos. Okay, it was a double well system. The state could be in this well or that. Nonlinear, but not chaos. But I can go up, and suppose I have a chaotic system, say a 3D system. Can I have a version of this logical stochastic resonance for a chaotic attractor? So what would I need? I would need a chaotic attractor to inhabit it, different parts of phase space. So, I would need an attractor which is in one part, attractor is another part, and they need to hop in a way so that I can encode a binary output. One always needs to have a clean way in which something is a 0 and something is a 1 at the end. Okay, so one could do that because you can have a system where an attractor sits here and an attractor sits there, and the trajectory can switch between these in a controlled way. So if I sort of make my inputs such that it switches exactly in accordance with the truth tables of the logic function, which I showed right in the beginning, and or XOR, etc., then I will actually have a kind of effective logic function from this chaotic attractor hopping. It works. That's not a surprise, but this was a surprise. The thing was that when we used chaotic attractor hopping, the input signal was, we could make it extremely small. See, in this business, if you have a very small input signal, it's good because it uses less power. If you hit it with a big signal, you get a big output, that's not so good, okay? So you want a small thing to yield a large result. So you would like sub-threshold, very, very tiny signals, and it should give an output which is, say of order of 1. So if this was of the order of 10 to the power minus 3, very small, size of the attractor, which is your output, was order of 1, then a very small change in the system gave this very different dynamical outcome. And so later, when I was talking to some friends who were telling me about tipping, so this is a phenomena in which a system can have huge dynamical changes through very small changes, either in parameter or state. So in some sense, this is it. Your attractor was actually tipped over by a very small nudge because of this, okay? So very small changes in the system, that is very low amplitude inputs gave highly amplified outputs. So it's even an amplifier, not just a logic thing. So that was the fun part of this thing. Okay, so that is my summary slide. I think I have done my 45 minutes. Yeah. So first thing I thought I would get across is that nonlinear systems are abundant in nature, and they also can be readily engineered and realized in the lab. Okay. In fact, if you look around, pretty much most things are nonlinear. You might kind of make approximations and massage something into a linear system, but a typical classical system is nonlinear. So the central idea is to exploit chaos or nonlinearity for the design of computing devices. So instead of wishing it away or suppressing it or saying, okay, what do we do? We have tried to use the opportunities which is embedded in chaos to do something useful. And in some sense, I should mention that it is actually a different approach from an engineer's approach, because I often go to engineering conferences. So one of the things which they have is, let us make the system cleaner and cleaner and cleaner so that it gets more and more linear. Okay, so that is the whole approach, to make it more linear. So, in a sense, we are jumping into the deep end like directly and saying, okay, just the full-blown nonlinearity, full-blown chaos, and then run with it. Okay, so it's literally the other end of this enterprise. So rather than, we have tried to do this. And what are the opportunities? The richness in the temporal patterns, because there are all kinds of patterns in it. The power of nonlinear transformations. There are things which a linear transformation just can't do. There are solutions which just will not exist if there were only linear transformations. And determinism, which we have used, because design would need us to work backwards and solve some equations to give you the lookup table or give you the parameters which will give you the right output. So this the design comes from the determinism. And the last bit was that if you throw in noise, as some people had been asking us to do, what if noise was there? What can you, how can you deal with it? So one of the ways is to, again, say that maybe there is a sweet spot of noise which will actually be good for us. So if there's a noise floor, we can go and sit in the right spot there and get the best possible performance. Okay, so this is noise and nonlinearity. And in some sense, I would say it is a constructive use of the jitters of noise, which is giving you better performance. So in that sense, it's a bit of a stochastic resonance-like phenomena, in the sense that there is a part of noise which is constructive rather than a destructive, which is the more usual way of thinking about noise. Okay, so that's all I had to tell you all today. And so I don't know how this is.
Somebody there? Yeah. Thank you very much. Very, very nicely in a way. I mean, you explained chaos in a very simple, and beauty of the simplicity of the beauty of the chaos was brought out. So very nice. And I'm sure people have questions.
Stunned
Feel free
everyone
to
into
ask.
silence.
I think they should ask.
Yes, please. Tell it. Yeah, hi.
Is it on?
Yeah, I can hear you, but maybe not the people at the back.
I was really interested by the last state. Hello. Yeah. So
In the last one?
no, this part
Oh,
only.
this.
The noise part. We
The
see.
noise part, yeah.
Can you just expand on that? Maybe?
Yeah, I can. Sure. Right. Okay. So if you okay, so let me put it a little bit like this. So what we have here is can I rub it up? Oh yeah, I've forgotten. H66. Yeah. True. Yeah. That's enough. So what I was saying was that if you have a system, okay, so you have a x dot some forcing function such that if I look at it as like a potential, it say has a double well, okay? Now, if I have a little bit of noise, so this is a stable state, this is a stable state, okay? So if there's noise, it can hop. Now, you are sort of trying to make the hopping such that with a bit of noise, it all comes to one state. So if there was no noise, if the noise is small, it will have a little jitter at the bottom, but it's still in this state. Or it will be like this. So if I look at the time series, it will be a little furry caterpillar, but on top here, something like this. But if there's enough noise, it can go from here and switch here because it's gone there. Okay, so this is expected. What you have to do is you have to adjust this noise window and the kind of bias because you're going to tilt it slightly this way and tilt it slightly this way so that your well is going to be a bit like this or your well is going to be a bit like this, depending on your input, so that your state is mostly sloshing around here or mostly sloshing around here. So one, say, is interpreted as output 1 and one is interpreted as output 0. So you want to, and what can do this for you? If I add a constant bias. So if you were doing an experiment, this would be a DC bias or something. Or if you're doing a numerical experiment, just add a constant. And if I integrate this out, I will actually get a swing. So your inputs are like this. I1, these are your inputs. So they are swinging your thing. And without noise, actually, this is still would be stuck here. But with noise, it manages to go to this thing. So it is a way of allowing it to kind of go to this thing, okay? I don't know if it is making...
So is it the noise that is making it deterministic at one
No,
point?
noise is noise. It's a delta correlated zero mean noise here. It's noise. I mean, you take it, if you were simulating it, you'll go to your computer and you'll take a random number generator and you will add it to your differential equation and simulate it. If you were trying to do it a little bit, might take it from a function generator from somewhere in a circuit and do it. So it is absolutely honest to goodness noise. Right? Without it, it's the one which is giving you a little bit of a jitter, right? So it's jiggling it enough that it can jump over once in a while. It's like if it is too little, it'll just be still sloshing here. It has to be enough to go over the barrier. And how high the barrier is what you have to do your calculation and find out. That is your design. That part is your design. So that you get the exact answer. So you know what you want. In hand, you have, C and I1, I2. That is what what your device is presented with. And noise is what you have, your noise floor. So that is the idea, a little bit. We could talk a little bit more later, maybe.
Anybody else?
Yes.
Hello, ma'am. Ma'am, in part one of MSc, we had one experiment, Feigenbaum circuit, and I believe this is also one of the examples in which
You have a
chaos.
Feigenbaum circuit?
Yeah, like
Means you have
demonstration.
a parameter, you
Yes,
see period
yes.
doubling. Okay.
So, ma'am, if I'm not wrong, as much like whatever I remember,
You
according
put
to
it
that,
at 4 or something.
yes,
Put it
yes,
at,
yes,
right,
correct.
right. Yeah.
So basically, bifurcations happen as we
Right.
change the
Yeah.
initial parameter. At
Correct.
one point, the system reaches chaos. Okay, and after that, when you continue to increase it, again we get 3 bifurcations.
No, no. Okay. I
I
think
mean,
a little
maybe
bit, yeah. So I probably don't remember it completely. So what happens is that there is an accumulation point, which is around 3.57-ish. So after that, what you get is chaotic bands, and you get windows, narrow windows of cycles, which are odd. So you get 5, 7, and a very big cycle with a window of 3. So that's the period 3, which Lee and York had, the famous one actually. So that's the 3 maybe which you are thinking, right? You said you'd see 3, right? After that, 4 is, that's around, I don't know, forget now, some 3 point something 8 or something. And after that, 4 is when you get a full chaotic circuit attractor between 0 and 1. So if you look at the probability distributions, it covers the entire interval, 0 to 1. That is the one which I'm working with, the most broad chaotic attractor. But you can get to that point, right? You can put it at 4 and try. Huh? Yeah.
Okay. Another question from this quarter or somewhere from behind? Yeah.
So, am I audible?
Hi.
So, you talked about classical systems.
Yeah.
Hold the mic closer.
Yeah.
Yeah, you talked about classical systems, right?
Right.
So, is chaos also observed in quantum mechanics?
Okay. I was wondering if I get this question, should I bail or should I give an answer? I'll give some answer. So one of the things is that personally, my entire thesis was quantum chaos. So that's how I started. But the whole thing is that it is, so none of what I said here actually I can translate, because this trajectory is not a thing which I can, uh, define in any meaningful way. There are attempts, of course. Everyone had it, especially in the 80s. So now you know when I did my PhD. But so there, people were trying a lot because it's an extremely interesting question, right? You see all this extremely different, qualitatively different classical behavior. Where is its signature in quantum mechanics? I mean, everyone will be wondering. So one of the ways to do it is to look at a quantum analog of a classically chaotic system and look for quantum mechanical objects which are different. So one of the things was statistics, level statistics. People were doing energy eigenvalue statistics, which would look like random matrix theory predictions. So that was one way of doing it. The other thing is, everyone's dream is to get a formula which has something totally classical on the right-hand side and totally quantum mechanical on the left-hand side, and to make. But well, there is one which involves periodic orbit sums and spectral density on the other side. But it is still not the scale. I mean, where, as I said, nothing which I have said here will go through in any of those things. And of course, now I know there's a revival, of course, of trying to look at the quantum analogs of things which could be, which are maybe classically chaotic. But yeah, I mean, so it's like Michael Berry would call this quantum chaology, in the sense he would say that the meaningful question is not to ask, is there something which looks like chaos in quantum mechanics? That's not the good question. He would say, try and ask a question. You stare at a system whose classical analog was chaotic and see if there's a difference. So that was how it is. And the only two differences main difference was in level statistics and all that. But I think he was not totally right. I think we should revisit that and try to get ways to understand it. But yeah, jury is out, I think, a little bit. Yeah.
Okay. No. It goes on YouTube, but before that, just if any of the other girls have any question, then we will come back to you.
Oh, okay. Yeah.
Okay. Then I'll ask.
I mean, this is an experimentalist's thing. So while certainly we don't see the exponential divergence of trajectories kind of chaos, but for example, practically when one makes quantum dots and looks at the photon statistics coming out of it, it is not determinate. It is essentially random, and sometimes people describe it as being chaotic. You can analyze it and get some kind of an exponent that you can use to characterize how random it is, though it is not showing this exponential divergence of trajectories like you see in classical mechanics.
So is the classical analog of this like a classical chaotic billiard or something? Would the classical analog of that be a chaotic system? So that is the only question. I mean, what is the classical analog of the system? I mean, we are trying to get a classical concept to match with a quantum thing. So, I mean, the hardest part is that bridge. Whether you have a nice way of getting a classical analog, but I mean, this is actually, of course, I mean, a very nice if one could, also work it backwards to the classical mechanics of it. Maybe I'd talk to you. Yeah.
Okay, so anybody else? Okay.
Yeah.
So Rajdeep, you have to it.
Young people.
I'm surprised
Hello.
all the questions for girls came from this side.
Ma'am, you
Sir.
told us about you told us about controlling the
Right.
chaos.
Yes.
But how do we actually do it?
Yeah, so that's what. So you have to have an idea, right? I mean, you can't, it's a chaotic system. It's extremely sensitive. So you have to have, so there are a few ideas. So I only gave you the one which was mine because, it's mine. But there are others. One of the ideas was to, which I didn't talk about, which someone else's, it's also a classic, is the thing is, one of the interesting things about chaos is that you observe this chaotic trajectory, but embedded in that, there are a dense set of unstable periodic solutions. You don't see them. It's like an invisible skeleton in your thing. So if you took a generic initial condition, it will always be, you'll only observe chaos. But these exist. We know it through calc. Now, what people have tried to do is to sit near those unstable things and give it push to balance it on these things. So these are called unstable periodic orbit control things. I personally think it's a very hard thing to do, and they are my friends, but I still feel that they are trying to push something which is hard to do. What I was showing is actually very easy to do, and the reason it works is that if you look at it, the stability of any orbit is given by, for instance, for this 1D map will be f prime at x1, f x2, etc., just a product. When you put a hard wall, there is one part where it's become zero. And if you have 1 0 in a product, everything is zero. It's magical almost. So because of that, just that act of thresholding actually makes it not just stable, but a super stable orbit. So you have thought of this. I'm sure you can think of others. The other things are, of course, parametric ones, where you push it to a window, which is a different parameter. But you're not controlling the chaotic orbit as such. You're pushing the parameter to a place where it's in a nice, like as you were saying, right? You take a Feigenbaum sequence, you push it to a window, then of course it is natural. That's also, some people would do that. Adaptive control is also done, where you sort of keep giving it signals which compensate for it going away. So if if it's running away from your the solution, if you give it a compensatory push backwards, it will come back. So it's sort of like balancing, a stick on your finger, like you keep, you've seen those clowns. I don't know. I've never seen them. I've seen videos where they sort of have a stick and how do you balance it? It's an unstable system, but you keep giving it a jitter. So, which will work. So it works a bit like that. So there are many ways of doing it, but roughly you have a chaotic system, and you have to think. That is where you come in. You have to think of some method which will do the work for you. It's not easy, but it's doable. Yeah.
Thank you, ma'am.
Okay.
Oh, okay. I thought so. I had a question
Yeah.
about this. At some point, Zurek had talked about, in the context of this chaos, you are looking classical,
Yeah.
quantum equivalent of classical chaos,
Uh-huh.
thinking in terms of some Wigner functions, and
Yeah.
making some very fractal patterns.
Yeah.
Has it followed up? I just know of that one paper. I don't know
Of
what.
course, that was that, or actually Husimi, which is what I like to do a little bit more, is even better distributed. So yeah, so that will sort of sit on the trajectory. So in that sense, it is I mean, it is a little bit more of has a thing. Yeah, but a distribution function is very hard to exploit. Yeah, but indeed, that is, of course, that people, especially for billiard problems, you can calculate it nicely. Yeah, so it is done. Wigner functions, Husserl distribution, these are the standard ones. Yeah, and they fall nicely on the trajectory. That it does. Yeah, yeah, that it does. Yeah.
Amul.
It's more of a curious question.
Hmm.
So, of course, you have a few patents, and you also mentioned some of them. What are these about?
Sorry?
What are they about?
What
The
is the
patents.
patent
What are the
about?
patents about?
Yeah, I know, because it was something. But the first one I had no idea, because some lawyer came and was doing stuff and whatnot. So the patent was the idea that you could put these, those solutions which I got, which has a certain set of thresholds, that you could, if you to put it in a electronic setup, to get all the logic gates. So that was the first patent. I think it's called method of getting logic gates through thresholding or something. So basically, that control method of ours is very potent. So of course, you can do the lookup table through exact analysis. So, but once you've done the hard work, you put it out as a. Then, of course, the thing is that someone has to do it in the circuit through that precision clipping circuit. And once you do that, then you say that this precision clipping circuit, which is a realization of the thresholding idea in theory, is your patentable object. So if you are going to do a threshold control with that, you pay us. Okay, or something like that. I don't understand the business so well, but yeah. Then, of course, once you do one, then every extra idea, you add another patent, and then suddenly you have 8 and you don't know what's going on. So, but it is basically something like you have a theory, and if it works in a proof of principle experiment, if someone wants to invest money to make a smaller, powerful device out of the same idea, they have to, well, okay, pay up, presumably. Yeah.
So I was just wondering, are these like restrictive to certain noises or?
Yeah, right.
Kind of noisy.
Yeah. Absolutely natural question. So the ones I showed you were delta correlated zero mean noise. And once this was out, the 5 Chinese group did all possible noises, colored, pink, brown, everything. So it works. So the bottom line is it works for all kinds of noises. I didn't do it, but a whole bunch of them have covered every possible noise.
So the optimality gets.
Optimum will be at different points. Yeah. Not actually as different as I thought also. I mean, the window is shifted a bit.
But it's very robust.
It's very robust. It is very robust. Yeah, that it is. Yeah. So those. I mean, we didn't check it. Lots of other groups have checked it actually. And there are lots of other experiments also, which I haven't mentioned. I only, just because I didn't had the slides of my own. Yeah, but others have done it with VXLs and all kinds of other things. I keep seeing it. Sometimes I don't understand also how they did what they did, but they say it's logical stochastic. But yeah, so there are many realizations also of it. In very not just electronic circuits, in optical systems and other systems, chemical systems. There were some I saw the other day, but because my knowledge is not so good of all these systems, I know they've done this, but yeah. But in theory, of course, I understand it fully. So yeah, that they have covered all bases. Yeah.
Thank you.
I think that is okay.
Okay. We will continue the discussion over tea. So first, let's thank Sudeshna once again for a wonderful talk.
Right.
And I want to add that VV 2025 team is extremely happy and proud to host your first professional talk since your PhD at TIFR. We hope the next one will be soon. She told us that, and we hope your next visit will be soon. So we go over to the West Canteen Terrace. We'll first have a group photo and then we have tea. Okay? All right. Thank you so much. Very good.